Let's talk about elasticity. This is a concept that comes up in health economics and economics elsewhere. And we've mentioned it before in the context of the demand for healthcare. This is a matter of looking at the percent change in Y due to the percent change in X. And it also comes up in the context of regression analysis. So elasticity, for example, price elasticity of demand, which we've talked about. In elasticity of -1 means that a 10% increase in price leads to a 10% decrease in demand. A -2 would be highly elastic or very price sensitive. -0.1 would be inelastic, which is not very price sensitive. And as we've talked about from estimates from the RAND health insurance experiment and others, the price elasticity for healthcare is about -0.2. So natural log of y. This is useful for lots of financial and economic variables. Some examples here: hourly wage, income, GDP, and of course healthcare expenditures are interesting to us. And this is the log scale of y, and a constant percentage growth, which is something we often care about in healthcare. How fast did healthcare spending grow over some period of time? A constant percentage growth is a straight line on a log scale. And that's great because we like lines in healthcare. Linear relationships simplify economic modeling. So for example, the Consumer Price Index, many of you may have heard of this. It's a measure of inflation. It's the cost of a representative basket of goods that some person might want or need to buy. It's used as a measure of inflation, which is just another way of saying growth in prices. And so let me show you on the next slide the graphs, both the levels and the logs for a constant 3.3% growth rate over time. So on this graph, in this graph on the left, this is just the level of the price, standardized, I think, around 1980. And so this graph on the left shows a 3.3% increase every year. And of course, 3.3% annual growth is an exponential curve. Everyone who's looked at population growth charts understands that 2% increase in population growth over time leads to exponential increase in the population. However, on the right, we're displaying the exact same data just on the log scale. And notice how that's a nice straight line. That makes things a little easier for regression modeling with ordinary least squares regression, because that's based on some linear assumptions. So we can make use of this handy feature with our regression modeling. So for example, we can model, as we did before, y equals 0.2x. And what we know from that is that a 1 unit change in x leads to a 0.2 unit change in y. However, we could also look at y equals 0.2 natural log of x. If this were our model, and if we got a 0.2 by regressing natural log of x on y, what that would tell us is that a 100% change in x leads to a 0.2 unit change in y. So when you're dealing with logs, you're talking about percentages. Otherwise, you're talking about units. Now, a 100% change in x is that would be a pretty big increase. And so oftentimes we don't see that. So another way that you can interpret it is you just divide both by 100. So a 1% change in x leads to a 0.002 unit change in y. This also works if we flip it around, and instead of having the natural log on the independent variable side, we can put it on the dependent variable side. So we take the natural log of y and run a regression with that. So suppose we ran a regression of x on the natural log of y, as in this third example, and then we get a 0.2 coefficient. That coefficient means something different. As you can probably guess, it means that a 1 unit change in x now leads to some percentage change in y. So a 1 unit change in x, because we're not logging x, we're just keeping it at its level value, leads to a 20% change in y, because y is in log terms. And finally, we can look at natural log of y and natural log of x. So it's possible to do a regression where the left-hand side variable, or the dependent variable, is a natural log, and so is the variable on the right-hand side. So looking at, in this case, suppose we get a coefficient of 0.2 when we're running a regression of natural log of y and natural log of x. What that means is that a 1% change in x leads to a 0.2% change in y. And now we're looking at a percent change in something leads to a percent change in something else, and voila, that's elasticity. So just for example, we've got 4 weight height models here, and these correspond to the models shown before. So we've got at the top here, we're looking at weight and height without any natural log terms. And as we saw before, this leads to a coefficient of 4.81, which means that a 1 unit increase in height leads to a 4.81 unit increase in weight. And then we drop down to these other models where we're looking at, here in the second model, we still have weight as the dependent variable. So you know that we're talking about unit changes in weight, but we've converted height to be natural log of height on the independent variable side, which will give us a different coefficient. I'll go over that in the next slide. And then here in the third model, we're taking the natural log of the dependent variable and keeping height in unit terms, or the independent variable in unit terms. And finally, down at the bottom, this is recognizable as elasticity. We've got natural log of weight and natural log of height, which leads to this coefficient. So I want to just jump right to that elasticity coefficient here. So we've got a 1.85 as a coefficient. That means that a 1% change in height, 1% change in our independent variable, leads to a 1.85% change in weight. That's another really useful way to look at this relationship between height and weight. It's useful to know that a 1 inch change in height leads to a 4.8 pound change in weight, as we see in this in this first model. And all of these have their applications. But the elasticity one is just sort of convenient because you can keep everything in percentage terms, and sometimes that's useful for what you want to study. There is a way to derive elasticity and to show that it has these properties that we're talking about. It's actually fairly straightforward. If you take a derivative, derivative of natural log of y is 1 over y, etc. I'm just going to pass on explaining this in any detail because I don't think anyone's going to be all that interested in it. But just for those of you who really want to understand the background, you are welcome to take a look at this or talk to me in more detail. I'm just going to pause here for a second.